let's do what we call the particle on a ring, right? Rotation in a plane at a fixed distance r. Classically, problem's been solved, right? All the energy is kinetic. The potential is zero everywhere, so we can forget about the potential. So the total energy is just equal to the kinetic energy, P being the linear momentum of the particle, M, of course, being the mass of the particle. Classically, again, the angular momentum is, now that would be the, we'll call it JZ up along here, right? Would be the cross product of these two vectors, the R and the P vector. And we're having rotation in a plane. So we can either have rotation go counterclockwise or clockwise, which is going to lead to this plus or minus P times R will give us the value of the angular momentum. Opposite signs corresponding to opposite senses of rotation. Classically, there's no constraint on the linear momentum and therefore no constraint on the energy and no constraint on the values of angular momentum. All of those variables would be continuous. What if we look at the quantum mechanical system? Well, quantum mechanically, what we have to do is first define the Hamiltonian. The potential is zero, so we only have to look at the kinetic energy term, which is going to be minus h bar squared over 2mr squared, mass, and the radius squared. Or we can express that in terms of the moment of inertia, I. Then we substitute that into the Schrodinger equation, and we have to solve for the wave functions psi that will satisfy this eigenvalue equation. What we find are the solutions given very simply by a normalization factor times an exponential I m sub j times phi. And you can, good exercises to substitute that back into the Schrodinger equation and indeed show that that is the case. So we've now found the solutions for the particle on the ring wave functions. Is there any constraint on m sub j? Well, let's look at the boundary conditions. And the boundary conditions are that, according to postulate 1, the wave functions must be single valued. Therefore, as phi goes all the way around our in the plane around the circle there, it varies from 0 to 2 pi, and angles, every time we put another 2 pi on there, we're getting back to the same point, right? So therefore, the we have to satisfy this boundary condition that the psi of phi must also equal the psi of phi plus 2n pi. And that can only be true if m sub j, what I've put in here is m sub j, is an integer, 0 plus or minus 1 plus or minus 2, and so on. What happens in the Schrodinger equation is that that has an effect on the energies, of course. The m sub j square values determine the energy, and therefore, if the m sub j values are quantized, so too is the energy quantized. Therefore, also, the projection of the angular momentum is quantized, plus or minus an integer or 0 times h bar. Oh, sorry. Okay. So quantum mechanically, we find a wave function, very simple wave function, but that wave function contains, we quantized along one coordinate, phi, we get one quantum number that determines both the energy and, in this case, the projection along the z-axis as well. All right, so we have our solutions. We have a quantized solution for energy and projection, right? There are only two projections in this case because we've confined it to rotate in a plane. And so we either rotate clockwise or counterclockwise. And the angular momentum for each state is quantized, as is the energy. You can look at this either as a model for rotation, that of a rigid rotor, because we've kept r fixed, or for orbital angular momentum, like an electron orbiting around a ring at a fixed distance from the nucleus. Now, unlike the particle in a box, where we were confined to a box, we're moving all the way around this ring here, and you'll notice that m sub j 0 is allowed. Therefore, the lowest energy state is energy of 0. There is no 0 point energy in this case because for that state, the ground state, it's actually spread out over the whole ring. And because it's spread out over the whole ring, the position is indeterminate, and therefore we can determine the energy exactly.